let's study 9th Standard ICSE Physics, Chapter 3b, Newton's Laws of Motion. So there are three laws, starting with the first law. We have to start with the concept called inertia. Now, inertia is defined as the property of an object by virtue of which, or because of which, the object continues to be in its state of rest or its state of uniform motion. You can think of it as the stubbornness of a mass. If there is a heavy rock, that rock will continue in its state of rest unless an external unbalanced force is applied on it. The reason why I say unbalanced is because if the force was balanced, that is, there were two forces or more forces which are equal and opposite, the net result is zero, then too this rock won't move. And it's a rigid rock, so its shape won't even change. But if the force is unbalanced, let's say this force was smaller, so there is a net forward force, then this rock will move. On the other hand, if we have a frictionless surface, frictionless, which is an ideal case because practically it's impossible to have zero friction between two surfaces. And if a ball was rolling on a frictionless surface with a uniform velocity v, now theoretically this ball can keep rolling till infinity if there is no obstruction in between because there is no friction. But in real life we don't observe that. We see that the ball will stop. Suppose you're on the grassy surface, the ball will stop after some time. But that's because there is friction. The object with uniform velocity will continue its motion unless an external unbalanced force acts on it. In this case, it is frictional force, which is always opposite in direction to the motion of the object. Or if there was a fielder stopping the ball, it is applying force on it. So this stubbornness of mass, due to which it will continue to be in its state of rest or it will continue to be in its state of uniform motion, is called inertia. It is an inherent internal property of any object which has mass. If you want to change the direction or the speed of a moving object, you have to apply a force. So Newton's first law states that every object continues its state of rest or of uniform motion in the same path unless an external unbalanced force is applied on it. So imagine you are in space. You are an astronaut wearing a suit and you are floating in space, which is almost zero gravity, and a push is given to you. So now you will start drifting away from your spaceship and you will keep on moving. There is no way you can stop because there is no friction or any external force. The physical cause of any change in velocity or change in direction of motion or change in shape or size is force. It makes sense to say that the heavier the object, more is the force required to set it in motion. Because the heavier the object, more is the inertia, more is the resistance to the change. For example, if you have two trolleys in a supermarket, one is empty and the other is filled with a lot of goods because you are trying to save or store as many things as possible in your household to last for the next 1 month. So we've got two trolleys and both are stationary at rest. Which one has more mass? The one filled with goods. So which one has more inertia? That same trolley, because inertia depends on mass. Inertia is a measurement of the resistance to change in state of rest or motion. So which one would require more force to be set into motion? The heavier one. So heavier the object, more force is required. On the other hand, imagine that both the trolleys were moving with a same velocity. So velocity is same and both of them are moving towards you. Which one would you find it easier to stop? The lighter trolley, because it has less inertia. So it can be brought to a stop with a lesser force. Now inertia is of two types: inertia of rest and inertia of motion. Inertia of rest is related to the fact that any object at rest would continue to be so unless an external unbalanced force is applied on it. Now there are some practical examples we can study about this. The first one, when a train suddenly starts moving forward, the passengers standing in the compartment tend to fall backwards. We have experienced this, and not only in a train, but even in a bus or any vehicle, if we are standing or for that matter even sitting. Initially, the train as well as the person is at rest. Now suddenly, this train moves forward. Since you were at rest, you had inertia of rest. So according to Newton's first law, you would tend to continue your state of rest. At least for a fraction of a second, your feet are touching the base of this coach. Since they are in contact with the base, they will also move ahead with the coach of the train. But the upper part of your body would tend to stay back in their original position. So for a fraction of a second, the lower part of the body would move with the train, but the upper part of the body would tend to remain in its state of rest. I said tend because don't think that the upper part of the body will stay behind and the lower part would move ahead. That's not possible. So for that fraction of a second, you feel the jerk and you move backwards. But then that force is transmitted to the entire body, and then you would continue to move with the train at uniform velocity. But the reverse is also true. What would happen if the train comes to a stop suddenly? More about it shortly. The second example is when a hanging carpet is beaten with a stick, the dust particles start falling out of it. So imagine we have this carpet. I'm giving you a side view of the carpet, and there are some dust particles attached to it. Now when you hit the carpet, at that place, the carpet shifts backwards. And you hit it so quickly that the dust particles had no time to prepare for this. They were astonished to find themselves hanging in midair. It's as if the earth was swept away beneath their feet. So when they look around, the dust particles, and they realize that they can no longer cling to anybody, they will fall down due to gravity. So why do the dust particles stay in the air? Because they had inertia of rest. That's why. Of course, this happens in a split second. They don't really have time to think about this. Let's take the example of the branch being shaken by a person. So very quickly the branch's position will change, but the fruit which was attached to the branch would not be able to change its position quickly because it has inertia of rest. So the fruit will remain as it is for that fraction of a second, but the branch has moved, so the contact between them is broken, and then due to gravity, the fruit will fall down. Another example is on striking the coin at the bottom of a pile of carom coins with the striker. The lowest coin only moves. This often happens assuming that there is hardly any friction between the coins because we've used some powder. So this is the surface of the carom board, and these are the coins one on top of each other piled. And with the striker, if we strike the bottom coin, that coin will move, but the remaining pile of coins will just move down and take that position. They will not topple. Why? Because they have inertia of rest. They will continue to be in their place. So they were in their place, but of course due to gravity they will come down. When a corridor train suddenly starts, the sliding doors of some compartments may open. Now, you'll have to use your imagination to visualize this. And you may have observed this in the local train. Imagine there is this coach of the train, and here are the sliding doors. Let's imagine that they are closed. Both the doors are closed. It is at rest. Now suddenly, if the coach moves ahead, however the sliding doors, this one would continue to be at rest. You see the frame of the doors is right in the center of the coach. So the frame of the door has moved ahead, and the right hand part of the door remains as it is, but the left part of the door goes inside the slot which was made so that the door can slide inside it. So here the door is opened. Where is the door here? It has gone inside, which is not visible because it is inside the slot. But why has the door gone behind? The door has not gone behind. The door simply wishes to be in its original position. The whole coach has gone ahead. The train has moved ahead, but we feel that the door has opened automatically. But the door has not opened automatically. The door which was here continues to be here, but the train has moved ahead. So we get the feeling that the door has opened automatically. Next, inertia of motion. So just like there is inertia of rest, we have inertia of motion, that an object in motion, uniform motion, will continue its state unless an unbalanced external force is applied on it. So some examples to understand this better are, number one, a cyclist riding along a level road does not come to rest immediately after he stops pedaling. So if you are pedaling and you're moving with great velocity on a smooth road and you stop pedaling, yet the cycle continues moving ahead. And we do this often to save our energy. But why does it move ahead even though we are not applying any force on it? Inertia. Objects can move even without force if they were already moving. The reason why we continuously apply force to keep things moving is to overcome the friction. If there was no friction, one push is enough for the cycle to move forever. Next, when a passenger jumps out of a moving train, he falls down. You need to be an expert while traveling in a crowded local train. Some of you might have to jump out while the train is still moving. Well, that is not advisable. But if somebody does that, if you notice, we are moving in a train, moving out of the train while the train is still moving ahead. Yes, the brakes have been applied, but the train hasn't stopped yet. And we need to get out of the train before the passengers start boarding the train. Otherwise, we would not be allowed to alight the train. So that is why some passengers might alight the train even though the train is moving. But that's very risky. And even here, there's a technique to do that. when we alight the train, when we come onto the platform, we need to make sure that we are facing the direction of motion of the train, and after we alight, we should continue walking in that direction. If we just suddenly come to a stop, we may fall forward, we may fall down. Why? When we are moving with the train, we have inertia of motion. The moment we step onto the platform, our feet are now in contact with the platform. The platform is at rest. The lower part of the body suddenly comes to a rest. A force was applied. But the upper part of the body tends to continue its forward motion because of inertia of motion. So the lower part is at rest. The upper part continues the forward motion because when we were in the train, our entire body was moving forward. So that motion will continue for that fraction of a second, even though the lower part of the body has come to a rest. So we tend to topple forward. So what is the solution? Well, as soon as you come down onto the platforms, continue walking some steps ahead and then come to a stop slowly. Decelerate slowly. If you try to come to a stop suddenly, you will topple. And especially, please don't get off the train facing in the opposite direction. You will fall head first. So you see how Newton's laws can help us travel safely as well. Third example is when a running car stops suddenly, or any vehicle, the passenger tends to lean forward. You are sitting in a car is moving with great speed, so are you. If the car stops suddenly, the lower part of the body in contact with the seat or in contact with the floor of the car will come to a stop immediately because it is in direct contact. But it takes a while for that force to be transmitted to the upper part of the body. So the upper part of the body, having inertia of motion, will continue its forward motion, and so we will get a jerk ahead when the car suddenly stops. And then once the force has been transmitted, for which we will have to apply more pressure on our feet to balance ourselves, then we will also come to a stop entirely. No, the upper part of the body won't be thrown forward, it won't be separated from the lower part of the body. That happens only in animated cartoons. An athlete often runs before taking a long jump. So if you've participated in long jump, you would notice that if this is the pit filled with sand, we don't just stand here and take a long jump. No, rather, a person would run with great velocity and then take a leap, and that way he or she would be able to jump to a longer distance. Why is that? Because if you're running, you have acquired a momentum, you have an inertia of motion. So when you jump, that inertia of motion helps you to continue moving in the forward direction in the air and makes you cover a longer distance. On the other hand, if you were just standing and jumping, then you would have covered a lesser distance. And finally, a ball thrown vertically upwards by a person in a moving train comes back to his hand. Suppose I throw a ball up. The ball comes down and I catch it. But suppose I'm in a moving train. The train is moving ahead at 100 kilometers per hour. When I throw the ball up, in 2 seconds the ball will come down, but in those 2 seconds the train, including me, would have moved ahead. So why wasn't the ball left behind? Why did the ball come back to my hand? Well, that's because the ball also had inertia of motion. So when you throw the ball up, it's not going vertically upwards. It's moving upwards as well as forwards. When you were holding the ball, along with you, even the ball was moving ahead at the speed of the train. The ball also was moving at 100 kilometers per hour forward. We couldn't notice it because for us it was at rest. But rest is a subjective property. So if from the point of view of a person on the platform, I draw a diagram, the person would see that the ball didn't just go up and come back down. The ball actually went forward. And after a couple of seconds, when you had already moved ahead with the train, the ball came back to your hand. So for you, the ball just went up and down, but for an observer on the platform, the ball moved forward as well, along with you. That's because the ball had inertia of motion. Let's start with Newton's first law of motion and inertia. All of this is cancelled. Galileo's law of inertia was an inspiration for Newton's law. Newton simply combined these sentences and stated that if a body is in a state of rest, it will remain in a state of rest, and if it is in a state of uniform linear motion, then it will continue its state of uniform linear motion unless an external unbalanced force is applied on it. You see, if an external balanced force is applied on it, then the net force will be zero, and still it will continue its state of rest or uniform linear motion. So only if it is an unbalanced force, then we can bring about a change in its state of rest or motion. And as we have already understood, the reason why an object continues to be as it is because of its inherent property called inertia. So this is cancelled. So the property of an object by virtue means because of which, it tends to retain its state of rest or of motion. That inherent property, internal property, is called inertia. Again, this paragraph is cancelled, and so is this paragraph. The definition of force has been explained and marked in the section A. So that's a better definition than this. Now we have a give reason out here. The greater the mass, the greater is the inertia of body. Because a heavier body is always more difficult to move or bring it to a stop. So mass is indeed a measure of inertia. There are two examples. One is of a cricket ball, which is easy to stop compared to a tennis ball if both are moving with the same velocity. That's because cricket ball is heavier. Similarly, if we have a loaded trolley and an empty trolley, it's easier to stop a loaded trolley if both are moving with the same velocity then. But this inertia is of two types. One is inertia of rest. The definition says that if a body is at rest, it will remain at rest unless an external unbalanced force is applied to it. And this property is called inertia of rest. And we studied various examples of that. So this is a definition, and then we have a give reason. When the train suddenly starts moving forward, why does the passenger standing in the compartment tend to fall backwards? That's because we were at rest, so we have inertia of rest. The lower part of a body starts its motion with the train, but the upper part tends to be left behind. Please write here, tends to be left behind. Similarly, when a hanging carpet is beaten with a stick, the dust particles start falling out of it. And on shaking or giving a jerk to the branches of a tree, the fruits fall down. Because when you shake a tree, the branches come in motion at once. Please mention the word at once over here. Similarly, even here mention at once. Because when the striker hits the lowest coin moves at once, while the remaining pile continues in its position due to inertia of rest. Similarly, in this example, right here at once. When you flick this card, smooth card, it will move at once, but the coin continues its state of rest due to inertia of rest, and then due to gravity it falls down. When a corridor train suddenly starts, the sliding doors of some compartments may open, because the train may have started, but the sliding door continues or tends to remain at rest due to its inertia of rest. Please mention of rest. So actually the door is not opening. It's just that the train goes ahead, and we see as if the door has opened automatically. Now, inertia of motion, mark this definition. Please add the word unbalanced force. Some examples have to be learned as GRs. Mark all of these as GRs. All of these, all the examples. The first GR is a cyclist riding along a level road, not uphill. He does not come to rest immediately. He continues to move forward even though he has stopped pedaling. Why? Because he has inertia of motion along with the cycle. And it comes to rest because of friction in the end. Similarly, when a passenger jumps out of a moving train, he falls down. Because as soon as his feet come in contact with the platform, they are at rest, but the upper part of the body continue to be in a state of motion because of inertia of motion. So what's the solution? Can you remember? I just explained it. Well, he should start running on the ground in the direction of motion of the train for some distance. Third GR, when a running car stops suddenly, the passenger tends to lean forward. Why? The same reason. When the car stops, the feet and the lower part of our body, the legs, they come to a stop, but the upper part tend to move forward because of inertia of motion. An athlete often runs before taking a long jump. Same reason, to acquire the inertia of motion. Add one sentence. As he has inertia of motion, he covers a longer jump. Of course, you can write she also. And the fifth give reason. A ball thrown vertically upwards by a person in a moving train comes back to his hand. Because not only are you and the train moving forward, but even the ball moves up and forward, so it comes back to your hand because it has inertia of motion. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.